So thank you very much for inviting me to come to this really wonderful event. I would like to especially thank Paula for tirelessly working on making my visit possible. And I also like to thank all the old friends, Lina, Manuel, and others, and for your wonderful hospitality. Thanks, student, for showing me very fantastic research result. And I'm also very glad to have this chance to share with you my recent research result. And of course, I'm presenting the result, but the real heroes are these people and who really made this research possible, and they contribute the results and of what I presented here. And as you can see, Paula is there, and most of them are my formal and current student and postdoc and colleague. So the drought, since I'm coming from California, you might hear the lots of news about California drought. But actually, drought is not just a problem for California. In US, since 1980s, and drought has caused about $200 billion of economic damage. Of course, US is not the only place who suffers drought. If you look at worldwide, this is just a snapshot I took in spring of last year, 2015, and I easily can find drought in many places on Earth. For example, at the time, the Sao Paulo has a few months of water left, and South Africa, Kenya, and Australia, as well as Taiwan, India. So drought is really a widespread problem worldwide. And current climate model has very large uncertainty in predicting recent drought, as well as observed dryness, increase of dryness. For example, here, this is a 2012 drought over US Great Plains, and this drought caused nearly $10 billion to US economy, also caused 24% surge of the corn price on the global market, 6% price surge of food on global market. But if you look at the NOAA prediction, they completely miss it. And over Amazon, the observation suggests that the wet season onset or dry season length has been increasing at the rate of a pretty alarming rate, about 5 days per decade, where none of the climate model could reproduce that participated IPCC fifth assessment, CMIP5, could reproduce this observed drying. So the critical drought prediction and projection is not only important for agriculture economy, but also very important in determining future regional ecosystem. In particular, if you look at this chart, that the area with rainfall between 2,500 to 1,000 millimeter per year, I think Colombia is within that region, and all the dry season lengths vary between 4 to 7 months. This region would be a region unstable for ecosystem. Unstable means small perturbations such as drought could trigger abrupt shift of ecosystem from, for example, forest to savanna. So about a third of the Amazon and the entire Congo forest is falling in this regime. And over the US Great Plain, US Great Plain is also in this unstable climate between savanna and the grassland. So here, a drought, a perturbation could also trigger abrupt shift of the ecosystem. So the question I hope to address here is what is the limiting factor for improving drought prediction and projection? In another word, why can't we predict or project the drought adequately? Is there any other source of predictability in addition to oceanic variability? We know we predict the drought mainly based on the El Nino sudden oscillation or ENSO. And however, that's important, but it's not sufficient to provide adequate drought prediction. And the second question is, what role does vegetation play in determining drought onset, intensity over tropical and subtropical land? Would vegetation memory provide more predictability for drought? So this is just to show this land seminal paper, Rapowski and Halpert, and they show that the ENSO influence over North and South American is about, basically, ENSO explain less than 40% of rainfall climate variability. And that is not sufficient for adequate drought prediction. So the take-home message of this talk, I hope I can present a case to show that vegetation can significantly influence the drought onset, intensity, and the duration through its influence on rainfall seasonality. Second, in addition to mitigate moderate drought, vegetation response to climate anomalies could hasten the drought onset, basically accelerating the drought onset, and lengthening the drought memory. Memory here just means persistent or duration. The length of such a drought memory may depend on depth of the root zone. I will not have time to present to you all the results given the limit of time, but I want to get this point out here. And vegetation climate interaction can provide additional source of the drought predictability. So first of all, let's see what caused the delay of wet season onset and drought over Amazon. The delay of wet season onset is a very important cause of the drought over Amazon. So therefore, understand the delay of wet season onset will contribute to understanding of the drought over Amazon. So the focus area I'm going to, the result I present is going to focus on southern Amazon. So this area, we have been seeing increasing dry season length. And this area, the dry season ranging from June to October. Wet season is November to May. The onset can change in between August to December. So you can see this is the largest swing of the onset, which really posed it's very challenging for agriculture planning. So the South American rainfall, especially over the southern Amazon, is controlled by monsoon mechanism. The classical monsoon we know is like, for example, Asian monsoon, is driven by, excuse me, increase of surface heating, especially over mountain elevated terrain, and that will create a pressure gradient between land and ocean. And this pressure gradient drive wind, trade wind from ocean to land, bring moisture to the land area, which support increase of rainfall. And increase of rainfall generate elevated latent heating, and that further drives circulation. So this is a classical monsoon circulation. Over South American, there's not enough of elevated plateau. The altiplano plateau is not big enough to drive this kind of a monsoon circulation. Instead, you have this vast area of the rainforest. So there's an alternative hypothesis put forward back in 2004, and actually by Wenhong Li, one of my former students. And we suggest by analyzing reanalysis data that increase of the evapotranspiration, or ET, at the end of a dry season provide moisture for increase of convection, the increase of convection produce elevated diabatic heating, which drive the trade wind or monsoon circulation, bring in more moisture from Atlantic Ocean, further enhance convection. So this positive feedback loop is causing the onset of the South American monsoon. So that's the hypothesis. And so how does that relate to drought or delay for wet season onset? So now if we composite, if we pick all the years between 1979 to recent years, say 2005, 2015, and we pick all the delayed wet season onset by more than 1 standard deviation, and we composite the anomalous circulation of these years. And so this is the composite result. The yellow-red color indicate anomalous subsidence, and the dashed curve indicate anomalous anticyclonic circulation. The solid indicate anomalous cyclonic circulation. So the onset usually in southern Amazon occurred between October, November. For late onset, it's usually November, even December. So although the delayed wet season onset occurred in end of year, but this circulation anomalies, for example, subsidence, can be traced back to the early of the year. For example, the March, April, May. In fact, the signal was much stronger in early of the year. So the question here is, so clearly we know that the ENSO influence or Atlantic sea surface temperature influence is stronger in boreal winter and the spring. So, excuse me, between January to say May. So this presumably is forced by ocean, but the question is what mechanism is maintaining such a long memory from beginning of the year to almost the end of the year? Is it forced by persistent ocean forcing, or is it caused by very persistent soil moisture memory? So the result I'm presenting will be trying to address these questions. So first, if you look at the literature, conventional wisdom always attribute to the delay of a wet season onset or drought to sea surface temperature anomalies, especially ENSO and tropical Atlantic variability. However, if you look at it closely, and the relationship, the correlation between ENSO or Atlantic sea surface temperature anomalies and the rainfall over Amazon, especially southern Amazon, is insignificant. And second of all, ENSO influence is strongest during December, February. Atlantic influence is stronger in March, April, May, strongest. But the wet season onset is in, most of the time is in October in Amazon. So what bridge this ENSO influence is not known. And the alternative hypothesis also have uncertainty. There's supporting evidence, there are uncertainties. So the alternative hypothesis we want to evaluate is we hypothesize that reduced rainfall and the recharge of deep soil moisture in previous wet season would decrease ET in the dry season and delay subsequent wet season onset. So the evidence that support this hypothesis is dry to wet season transition is initiated by increased humidity in the atmospheric boundary layer, so coming from surface, instead by reverse of monsoon circulation, as I presented by cartoon early. Also, Amazon rainforest increased photosynthesis, thus ET in late dry season, driven by leaf development instead of by climate. So this has been published, documented in literature pretty consistently. However, there's also uncertainty. For example, if you look at the correlation between moisture convergence and the rainfall, you always find that that correlation is stronger than the correlation between ET and the rainfall. Second, whether ET is responsible for increasing moisture not only in the boundary layer but above boundary layer during the dry to wet transition is not clear because we don't have adequate observation. Oh, thank you. And so we need to at least clarify these questions before we can, for validating this alternative hypothesis. So how do we do that? Over South America, the meteorological measurement from the network, like radio sound, are relatively sparse. So doing the moisture budget analysis using real analysis is not reliable because that is mainly model result. And so therefore, we need other type of data. So one powerful constraint one powerful data is the water vapor isotope, the deuterium of the water vapor. So this can be measured can be measured by satellite observation. So how is a deuterium, or we call HDO, of water vapor can help us determine the source of water vapor? So we know that when the water vapor is evaporated from ocean, and evaporation tend to take the lighter isotope and leave the heavy isotope behind. So the water vapor coming from ocean evaporation is lighter. And as it travels from ocean to land, and it experiences condensation, re-evaporation, precipitation. Every time you condense vapor, generate cloud rainfall, you preferentially remove the heavy isotope, leaving lighter isotope in the air, in the vapor. So as the air moving from ocean to inland, you will find the heavy isotope become more and more depleted. So therefore, you will see that the HDO become increasingly less or depleted as you travel from ocean to land. However, the vegetation does not fractionating. Vegetation take the soil moisture, push through its stomata and release in the air. It does not fractionate the vapor. And therefore, if the water vapor is coming from transpiration, you will see a very enriched HDO. And if water vapor coming from ocean, you will see very depleted water vapor. So here is an example of satellite oral test satellite measurement of HDO. And you can see that when this is the track. So over the US continent, the HDO is in the above boundary is rather depleted here. But as you fly over Amazon, all of a sudden you see this big pause of heavy water vapor with a heavy isotope. So this is an indication that water vapor over Amazon is mainly coming from transpiration, not from the ocean. So how do we use this data to determine what drives the dry to wet season transition? So here we use a suite of satellites. And so the top here, the rainfall here is a trim. And this is sun-induced fluorescence. It's a better indication of it's more direct indication of photosynthesis than the NDVI or EVI. And this is the equivalent potential temperature and the saturation equivalent potential temperature plot. And this is let me explain. This is a time, and this is a height. And this coming from AIRS satellite data, which gave you temperature humidity profiles. And the cloud coming from Terra Aqua. And also this HDO regression with water vapor is coming from Aura satellite. So there's 5, 6 different satellites are involved. And so now let me explain the variables. And this is evapotranspiration, precipitation, moisture convergence. The background is solar radiation. And the moisture convergence and the ET are derived from ECMWF interim real analysis. And this is fire emission of the CO2 and obtained from combined satellite and modeling product. And the cloud and the regression of the HDO against the water vapor tells you what is the source of increasing moisture. And if you see a positive, if you see a positive slope, and that means the HDO increasing, and that means you have more water vapor coming from plant transpiration. And when you see positive reduced slope, that means the water vapor is increasing, become more moist atmosphere due to the plant transpiration. And if you see negative slope, that means the water vapor coming from ocean, because negative, you see decrease of HDO. So finally, what does this chart mean? This chart is a composite pentate evolution of the dry to wet transition. This line is wet season onset, and each line here represents 1 month of the time. And so this is like 2 months before onset, 1 month before onset at the pentate level. So now let's look at the evolution of the wet to dry transition. So about 2 months before wet season onset, you begin to see increase of photosynthesis, increase of evapotranspiration. And then, so this increase, this is occurred with increase of low cloudiness, shallow convection, and the increase positive but a decrease of the HDO versus water vapor. So what this suggests is the increase of photosynthesis, ET, and the increase of a shallow cloud is pumping a lot more transpired water vapor enter the lower troposphere. And this is a tropospheric water vapor HDO versus the water vapor amount. And so the transpiration, increase of transpiration is mainly responsible for increase of humidity and the increase of stability, convective instability in the lower troposphere. And so we can also look at the spatial distribution of the water vapor and the wind. and the HDO and the moisture convergence here. So 2 to 3 months before onset, this is like a pre-transition season. And you see higher humidity in the western Amazon, lower in the east, and the wind coming from ocean. But so if you look at the HDO distribution, this brown suggests depleted HDO or oceanic source, water vapor of oceanic source. The green color indicate enriched water vapor with enriched HDO. This suggests water vapor coming from plant transpiration. So when the transition season start, which is 1 to 2 months before onset, and you find the increase of water vapor in the lower troposphere associated with the increase of HDO, this suggests the increased water vapor is due to transpiration instead of ocean, coming from ocean. And 1 month before onset, the moisture increased further, and the HDO enriched more, which means more and more water vapor coming from plant transpiration enter the lower stratosphere. After wet season onset, the moisture is very high, but during the wet season, the moisture is mainly coming from ocean. So what about shallow convection, the role of shallow convection? So the evapotranspiration only provide water vapor for boundary layer. To transport water vapor from boundary layer to lower troposphere, you need a transport mechanism. So here we show using the Go Amazon data. This is the radio sound data, combine the radio sound data and W-band radar data. So we use W-band radar, cloud radar, to determine whether there is shallow convection occur or not. And this figure shows you the changing of the moisture after occurrence of a shallow convection minus clear sky. So you can actually see that after increase of shallow convection, you see moistening of the lower troposphere. So why is increase of lower tropospheric moisture important for occurrence of deep convection? This is actually very important conditions, thermodynamic condition for increasing convection, mainly because if you have a very humid, buoyant air in the boundary layer, and as this air rising towards level of free convection, and it will exchange with the ambient environment. If ambient environment is very dry, and this air partial is going to be diluted, and in terms of moisture and in terms of buoyancy, and therefore this air will not be buoyant enough to make to the level of free convection. So you need to have a humid lower troposphere to prevent dilution of this rising convective parcel in order for deep convection to occur. So finally, the shallow convection, the increase of transpiration, shallow convection, is creating a thermodynamic condition favorable for increase of deep convection. But to actually make deep convection happen, you need a dynamic lifting mechanism, and that is cold front incursion. You can actually see trim animation, trim data animation every time. The way increase of convection is really following these cold front. And so that's how, and then the increase of deep convection produce increase of the latent diabatic heating in the middle upper troposphere, and that drives the reversal of the monsoon circulation. So that's the mechanism involved in dry to wet season transitions. So the timing, I would like to emphasize the timing of increase of photosynthesis is crucial for dry to wet transition. The reason is the following. If you look at the cold air incursion, in this case, we use the sea level pressure to, that's a solid line. I apologize for the quality of the figure. And so the solid line, every time you see a spike of increased sea level pressure, and that is cold air coming into southern Amazon. And the dashed curve here is the surface temperature, and associated with cold air, you see a sharp drop of surface temperature. So these are the cold front incursion event. You can see that during the dry season, the cold air incursion is stronger and more frequent. But yet, you don't have rainfall, so this is a rainfall. And that is because the humidity of the atmosphere, especially lower troposphere, is low. And so as the time goes from dry to wet season, the humidity begins to increase. You see here this curve. But the cold air incursion becomes less intense. So the increase of ET here right before cold front incursion become too weak to provide a larger scale convection is very crucial. And so for example, if the increase of ET is too late, then there will not be enough of a cold air incursion to provide a large scale lifting. So, here, the wet season initiation of the dry to wet season transition is really a result of rainforest seasonality, the growth of the rainforest new leaves, and the large-scale meteorological condition. They work together to lead to the onset of the wet season. And here I want to show that as you see increase of convection and the rainfall during transition season, you actually see the latent heating in the atmosphere increasing progressively, and that provide the energy needed to drive the reversal of the monsoon circulation. So here I want to summarize those results using cartoon. So the dry to wet season transition is initiated by increase of evapotranspiration and photosynthesis, and that increases surface air buoyancy and the convective available energy. And then the cold front coming in lift these moist and buoyant air and increase of deep convection, which produce elevated diabatic heating that drives the deep tropospheric monsoon circulation reversal and the moisture transport from Atlantic Ocean. So this positive feedback leading to the wet season onset. So why does the delay of the wet season onset starting with rainfall reduction in previous wet season? And the reason we think is if we look at this soil moisture data analysis, this is a formal postdoc of my Robinson Negro Schwartz, and where he analyzed the soil moisture data over Jaru, southern Amazon. What he find is, so the top is rainfall, and this black histogram is ET, and this gray column represent the dry season. And the middle column shows you the net ecosystem exchange, which is a net carbon flux, and the vapor pressure deficit. And the bottom shows the soil moisture, so from shallow to deep. So what you can see is during the wet season, and the soil moisture, the photosynthesis are low, and the soil moisture recharges starting from shallow soil and propagating to deep soil. So the deep soil is really recharged at the end of the wet season, previous wet season. So as you enter dry season, the increase of photosynthesis is using up surface soil moisture first, and then gradually they start to use deep soil. And during the wet to dry season transition, they actually use the deep soil moisture to support the photosynthesis and the increase of ET. So therefore, if you reduce rainfall in the previous, at the end of a previous wet season, you are reduced recharge of the deep soil moisture. And this deep soil moisture will in turn reduce the increase of ET in the transition season. And therefore, this is a very deep soil moisture memory that allow the drought signal occurred in the February, March, April to actually stored in the deep soil and resurface in later of the year from September, October to November. So here, I like to use a cartoon to summarize the cause of the delay of the wet season onset. And so rainfall is reduced in May, early of year, which reduce deep soil moisture. And the deep soil moisture in turn reduce ET during the transition season. And the drier surface would reduce shallow convection and increase the surface solar radiation, which further dry the surface, as well as reduce the moisture transport from boundary layer to the lower troposphere, and that reduce deep convection. The deep convection reduce deep convection would reduce diabatic heating, and which delay the circulation reversal associated with monsoon onset. So really, this is a very long memory. Basically, it's 6 to 8 months of the dry anomalous memory are a result of two memory sources. One is deep soil moisture that gives you about 6 months of memory. And then the coupling between surface, shallow convection, and deep convection, and the large scale circulation give you another 2 to 3 months of memory. So together, we're getting 6 to 8, even 9 months of memory. Of course, the dryness during the dry to wet transition period really have a strong effect on fire, and which in turn affect aerosol and affect the rainfall. So the delay of wet season onset is a result of interplay between large-scale meteorological condition, land surface, fire, cloud, rainfall interaction. So can we use this understanding to explain the delay of the wet season onset? So this figure shows you the relationship between convective inhibition energy, which is connected to land surface dryness, and the latitudinal position of the subtropical jet. So if you if you see subtropical jet here, that's a poleward displacement. If you see larger cine, that's a drier land surface. So the red means delayed, late onset, green means early onset. Almost done. So you see the most of the delay of a wet season onset is associated with dry surface and the poleward shift of subtropical jet. Almost done. So of course, I mentioned that drought is not limited in South American. Over U.S. Great Plains, we have been hit hard by drought. And I don't have time to go into detail except to say, despite very different climatology, very different vegetation type, the mechanisms that cause drought are surprisingly similar, and the processes involved are surprisingly similar, except over the Great Plains, you have a very shallow root and less vegetation, therefore the soil moisture memory is shorter. And so now we show that vegetation is not just respond to rainfall. It actually actively regulating rainfall anomalies. So would this imply the impact of vegetation on drought? actually can increase the vulnerability of the ecosystem to abrupt change. And the conclusion, vegetation not only respond to climate and drought, but also actively regulate drought through its influence on evapotranspiration and soil moisture. In particular, over Amazon, it mitigates moderate drought, but it provides interseasonal 3 to 9 months memory that connect the ENSO at the Atlantic influence on rainfall in boreal winter to spring to wet season onset in boreal fall and through rainforest nodes. Over U.S. Great Plains, it actually accelerates the onset of summer drought by increasing photosynthesis and deplete soil moisture in response to warm spring. So the implication here is the land use may delay wet season onset and lengthening the dry season length. Final remark, done. And so the final remark is human has trying to predict the weather, including drought, at least since Babylonian time, that's millennia ago. Yet predict drought for more than one season was not possible until in 1980s we were able to predict ENSO. The next leap for improving drought prediction and projection will depend on our ability to understand and predict ecosystem response to climate variability and change and their impact on drought, especially over tropical, subtropical continent. I would like to thank you for listening to my talk. Thank you. Gracias.
Hi, Rong. Thank you for this wonderful talk. What do you think it will happen in future when we have increased CO2 concentrations in the atmosphere, but we also have enhanced land use change, especially in the Amazon?
Yeah. Thank you very much for the question. I think it would, based on our understanding, it would delay wet season onset for two reasons. One reason is a very a quite well-established study, quite established climate global warming effect is the poleward shift of subtropical jet. And that will reduce the cold front incursion into southern Amazon. And that will reduce rainfall during the dry transition season and delay wet season onset. The increase of land use will reduce the ET during the dry season and the transition season, and that basically will cut off the moisture increase you need to initiate dry to wet season transition.
Rong, do you know any study that has used modeling to test your hypothesis of this interaction between evapotranspiration and the starting of the life cycle evolution of the clouds?
That's a very good question. Indirectly, in terms of testing influence of deforestation on rainfall. However, I think they do show delay of the wet season onset, reduced rainfall. But I would like to cautious the way convection is treated in global climate model. Basically, it doesn't care surface. And therefore, the sensitivity they represent is very questionable. I think that's why not a single climate model simulation could reproduce the observed dry over the Amazon. So, I think in this case, the adequate representation of the relationship between convection and land surface is crucial. But unfortunately, most of the cumulus parameterization are developed based on observation over oceans, ITCZ. So over land, that is problematic. So.